Let's try this in a situational problem. There are 20 seats in the front row of a theater. Each successive row contains 2 more seats than the previous row. If there are 21 rows, how many seats are there in the last row of the theater? What is the total seating capacity of the theater? If we add the numbers in an arithmetic sequence, we get the sum called series. For example, if you have the arithmetic sequence 1, 2, 3, 4, and 5, solve for the arithmetic series or find the sum of all these terms. You simply add them all, right? The sum is 15. But what if you are asked to find the sum of the number sequence 1, 2, 3, 4, 5 until 100? What? Layo nun. Teleportation is useless. There must be a shorter way for this. Guys, you know what? It's a grade 4 pupil who figured this out. A 10-year-old boy. What's this?
A great example of someone who was able to see the mathematical patterns around him is Carl Friedrich Gauss. In 1787, young Carl was a 10-year-old student in Braunschweig, Germany. The pattern that was perhaps most apparent in his class was the tedious repetition of a dismal life. There was an instructor at the school by the name of Büttner. Although he enjoyed intimidating his students, Büttner often found that teaching involved too much work. He therefore devised ways to keep his students busy for hours on end while he sat back to relax. On one occasion, as the story goes, he gave his class the task of adding together all the numbers from 1 through 100. This, he had hoped, would earn him a relaxing afternoon of watching students tap away at their slates. He had barely finished his instructions when his student, the young Carl Friedrich Gauss, stood up from his desk, walked up to the front of the room, and turned in his slate on Büttner's large desk with an offhanded, "There you go." Young Carl sat quietly for the rest of the afternoon as his fellow students finished their addition, and Büttner planned how he would beat his arrogant student for avoiding his classwork. One by one, the other students finished and placed their slates on top of Carl's. When all of the slates were turned in, Büttner immediately ripped Carl's slate out from the bottom and looked at it. To his astonishment, he found that Carl had the correct answer, and the only number on his slate was the answer. He had written no calculations whatsoever. How did he do it? How had he figured out how to avoid such boring, repetitive work and still produce the correct answer? Let's see if we can start to find a pattern to Büttner's horrible addition task. If you start writing out the numbers 1 through 100, or even start punching them in on a calculator, you should notice a repeating pattern. If you look at the problem in chunks, you are adding together the single digits 0 through 9 a total of 10 times, and adding together 10 tens, 10 20s, 10 30s, and so on. The addition problem may seem daunting when you first look at it, but once you start solving it, you can see that it's just screaming out with possible patterns. It's not completely clear what approach Gauss actually used, but more than likely, with the speed at which he solved it, he probably thought along these lines. Let's think of all the digits as being drawn out in a long row end to end. On the far left is 1, and the far right is 100. If we add the first and last number in the sequence, 1 and 100, we get 101. If you look one step in from these numbers to 2 and 99 and add them together, you also get 101. Move in another notch to 3 and 98, and they also total 101. This pattern continues throughout the sequence of numbers until we meet at the center with 50 plus 51 equals 101. we've seen that arithmetic statements can also be encoded with shapes. To make the pattern perhaps a bit more obvious, let's picture the numbers 1 through 100 as little squares. The number 1 is represented as 1 square, the number 2 as a stack of 2 squares, the number 3 as 3 squares, and so on. All the numbers stacked up one next to the other form a sort of triangular staircase. The task now becomes to count the total number of squares. Previously, we used multiplication to determine a number of tiles arranged in a rectangular shape. But now we don't have a rectangle, but a triangle, which we don't yet know how to deal with. Perhaps we could find a way to turn this triangular shape into a rectangle. We could divide the triangle into 2 parts right between 50 and 51. We could then take those 2 chunks and fit them together like puzzle pieces to form a rectangle. The single square is moved on top of the stack of 100 squares. The 2 squares are on top of the 99 squares, and so on, all the way down to the 50 squares on top of the 51 squares. Moving around this piece hasn't changed the total number of squares. We simply worked to rearrange it into a form we could more easily deal with. The figure is now a rectangle that has 50 squares across and 101 squares running up the height. Multiplying 50 by 101 gives us the total number of squares, 5,050. When we look at the problem in this way, we see that it isn't a hassle to add together any series of numbers. Let's look at the diagram and see if we can find a general description for the pattern. The height of the rectangle is the sum of the first and last number. The width of the rectangle is the total number of digits being added, divided in half. These 2 quantities define the edges of our rectangle. To find the area of the rectangle, we simply multiply the height by the width.
Here's the formula from Gauss. S sub n equals n over 2 times a sub 1 as the first term plus a sub n. Sn is the sum of the arithmetic sequence called series. N is the total number of terms to be added. A sub 1 is the first term and a sub n is the last term. We know that a sub n equals a sub 1 plus the quantity n minus 1 times d. We can now substitute the right side of the equation here. Simplifying by adding the 2 a sub 1s together leads us to an alternative formula for the arithmetic series. And that is S sub n equals n over 2 times 2 times a sub 1 plus the quantity n minus 1 times d. For your performance task, let's do the Pringles challenge. Here's my sample savings scheme at the beginning of this video. My initial deposit is 20 pesos. My regular deposit is 5 pesos a day for 240 days as my N. How much will be my savings after 240 days? Substituting all the given to our formula, my savings will be 1,215 pesos. Not bad, right? Now it's your turn to have your savings scheme. It's up to you how much will be your initial deposit, how many days would it take, and how much will be your regular deposit. You can have it daily, weekly, or monthly deposit depending on your capacity to save. That's all for now. I hope you learned something today about arithmetic sequence, arithmetic means, and arithmetic series. Congratulations! See you in our next video lesson. Stay safe, stay home, and stay productive. Save for the rainy days. Good luck to our Pringles challenge. God bless. Bye-bye.